Good afternoon, everyone. It's my great pleasure to welcome all here in this particular session on coastal and environmental geotechnics. So let's give a warm welcome to our session chair, Dr. S. Sridevi, and co-chair, Dr. Swagata Mukherjee. So our chair, Dr. S. Sridevi has been currently serving as Vice Chancellor for C.V. Raman Global University in Odisha. She has been working for more than 30 years in academics with the specialized area in the geo-environmental engineering and soil improvement. So apart from her, we are also having Dr. Swagata, who have been recently joined IIT Madras as assistant professor, and he will be co-chairing our session. Before joining to IIT Madras, he has worked in IIT Bombay as postdoc and IIT ISC as a research assistant. So he has completed his education from Yadavpur University as BTech. Apart from BTech, Masters and PhD he has completed from ISC. So I would like to welcome our session chair and co-chair to come on the dais and attend it. So now I would like to hand over the session to our chairs and co-chairs. So they will be introducing our thematic lecture, Professor S. Sridevi.
Good afternoon, everyone. Welcome to first Geo-Asia conference. Today we have with us the theme speaker, Professor Srideep Shekharan. He's a professor in Department of Civil Engineering, Geotechnical Engineering Division, Indian Institute of Technology, Guwahati, India. And sir is going to present on the topic, engineering the unsaturated soil behavior for agricultural drought preparedness. Now, sir is well known to everybody, but for the benefit of few of the audience who are attending for the first time, I would like to introduce sir. Dr. Srideep is currently a professor in the Geotechnical Engineering Division, Department of Civil Engineering, Indian Institute of Technology, Guwahati. He obtained his PhD and MTech degrees from IIT Bombay and BTech degree from Calicut University. His research interests include behavioral studies of unsaturated porous media, climate change impact on soils, hazardous waste management, then utilization of industrial and agro waste, and geotechnology. Now he has published more than 150 journal papers, and he was a recipient of Shamsher Prakash Research Award for Geotechnical Engineering in 2014. He is a member of ASCA, ASTM, IAS, MAG, IGS, and TC 106 of ISSMG. Now I will invite Professor Srideep to give the presentation.
Good afternoon to all of you. Thanks for all the audience and to the chairs and tables. I hope they will also listen to my lecture. So today, Madam has already introduced me. Thank you for that. I'll be talking about engineering the unsaturated soil behavior for agricultural drought preparedness. This falls basically under the category of climate change impact on soils And it confines to the theme of environmental geotechnics. So let me move on with the lecture. This is the overview of the presentation. First, we will be understanding what is agricultural drought, how soil moisture is related to agricultural drought and how it is measured, how it impacts, how the drought condition impact soil and plants. Then what is the relevance of soil moisture in unsaturated soil behavior? Then what is meant by, when you say engineering the unsaturated soil behavior, what do you mean by that? And how to engineer it? And followed by what are the research focus for future? So let's understand a bit about agricultural drought because that's very important. We all would have heard about what is drought, but there are different types of drought classifications, one of which is agricultural drought. And you say in terms of agricultural drought because it impacts the growth of plants and to some extent the availability of food. So here agricultural drought, it is referred in terms of soil moisture. And then because plant grows in soil, it would impact the plant growth as well. So whenever soil moisture impact and plant growth is studied as an action of drought, it comes under the definition of agricultural drought. So due to prolonged arid and drought condition, soil moisture is lost by evapotranspiration. Most of the things are very close to what is happening around us, and so one should be able to connect it well because these are all common facts. So soil moisture is lost by evapotranspiration during the dry period. So what happens is the plant is not able to extract moisture from the soil and it becomes dry, it wilt, and it impacts the growth of the plant, and ultimately it impacts the crop yield. So soil becomes dry with soil moisture approaching zero, plants not able to extract water from the soil. So this causes loss in vegetation and reduces crop yield. So for arid and semi-arid regions, those who have basically from those regions will be able to understand the gravity of this problem better. Those who are from water surplus region would not appreciate much in the current context, but the problem is a bit futuristic because we are leading towards a situation where we won't have adequate amount of water, both domestic as well as agricultural. So there has to be strategies coined to tackle this well in future. So for arid and semi-arid regions that cannot afford frequent irrigation, agricultural drought can reduce productivity and it affects the food security in general. And it also has other secondary cascading effects because once food becomes a problem, it's going to impact socio-economic setting, ecology, health, nutrition, morbidity, everything comes as a chain reaction. Just to give a glimpse of how droughts look like, because we as geotechnical engineers may not be that well versed with this. From the year 1871 to 2015, India witnessed 25 drought years. And with droughts occurring between 65 and 87, almost 10 droughts occurring in that particular time frame. So this is taken from this reference. In 2002, this is as per the statistics given in this reference. 300 million people spread over 18 states were affected by drought, I mean in Indian subcontinent. In 14-15, 15-16, the significant part of the country was affected by drought. and the figures are not very good in the global scenario as well. And now it is further compounded by the issues of heat waves, wildfire, and in general, the issue of global warming. So that is one part of the story. The second one is, where does it impact the more? So it is in terms of soil moisture, and this is where our subject of interest is. So generally we all know soil moisture is defined in terms of gravimetric moisture content, which mostly geotechnical engineering, we are well versed with that. It's also defined in terms of volumetric moisture content. That VMC is very important for all of these geo-environmental studies. So I'll be focusing more on VMC, because GMC, all of us know. This is the popular three-phase system of soil, which is defined both in terms of mass and weight, volume. So one is weight basis, that is gravimetric, which is a very popular moisture quantification. And VMC is on volume basis, and it is those who are not aware of that, I'm just explaining. VMC, or it is very popularly represented as theta, is defined as volume of voids upon total volume, very close to the definition of porosity. So the relationship, there's a relationship between both GMC and VMC, which is expressed as theta is equal to rho d by rho w into GMC, where rho d is the dry density of soil, rho w is the density of water. And if it is in density, it is 1 gram per cc, because many of the literature sometimes write in this form, VMC is equal to rho d, which is in fact not correct. This is only true when rho w is 1 gram per cc. It is also defined as VMC equal to degree of saturation into porosity. That's very clear if you see the above definition and this, when degree of saturation is equal to 1, VMC is equal to porosity. This part of the definition is very important as we go forward. When we talk in terms of soil moisture, the last one is very important to know. VMC is equal to porosity when degree of saturation is equal to 1 or 100%. Why? Because porosity is volume of voids upon volume of voids. When all the voids are filled with water, it becomes VMC. So the definitions are more or less same. Why VMC is important and how it is measured? There are significant developments that has happened in the last few decades. So we have electronic sensors for measuring VMC, and that's the advantage of VMC. Why? Because many a times you need to measure the water's content status over a period of time, and that need to be measured continuously. So this is not possible in the case of gravimetric moisture content. Every time you cannot afford to dig out the soil and keep repeating the measurements. Here, if it is in terms of sensors, you can deploy the sensor in the field and you can data log it and you can just leave it. So everything is done automatically. So you have a continuous variation of moisture available, which is in fact very important for drought kind of studies or climate change impact studies. So it facilitates non-invasive and non-destructive measurements in the laboratory and field. So it is essential, VMC is essential to quantify the soil moisture status. Because once you know what is the soil moisture status, you can track the progression of agricultural drought. So what is the basic physics of measurement? Because it is VMC measurement is based on the electrical properties of the soil. How it is connected? Because the electrical property here is defined in terms of dielectric constant. So dielectric constant of a dry soil is generally in the range of 3 to 5, whereas water, it is close to 80. So a combination of when water comes into the soil, you have a very large margin ranging from 3 to 80. So this aspect is used for measuring volumetric moisture content through a proper calibration. So it is correlated to VMC. So there are a wide variety of VMC sensors available, which vary in terms of cost, performance, accuracy, and operational frequency. These are some of the market available sensors. So next we will move on to global warming and AD impact on soils. So agricultural drought, the major impact is on the soil moisture. So soil moisture has a major role in sustaining all the life activities on the planet. So it starts from the microbiological aspects that happens in the soil to the macro life. So a prolonged loss of soil moisture in the soil is an initial sign of desertification. So over a duration of time, it prolongs, then slowly the process of desertification starts. The pattern of soil moisture, it has got some correlation with the local precipitation. These are the recent studies. Soil moisture precipitation correlation, it is dependent on factors such as vegetation, land cover, climate regimes, so on. So such a feedback, it also influences the water and energy cycle, which actually sustain all of these life on the planet. Soil moisture loss, it negatively impacts the soil carbon storage. So depletion of soil moisture, it in fact aggravates soil degradation. And when I say soil degradation, it's the overall soil health with low nutritional value. This would definitely impact food insecurity. So this would lead to we missing the milestones of SDGs. So essentially, the Sustainable Development Goals of United Nations. Third is zero hunger, and fourth is good health and well-being. So both of these targets we will miss. So for that, there need to be some proposal on some hybrid solutions to preserve soil moisture to the best possible. This was done in the past. This was happening naturally over a period of time, but then nowadays that's not the situation. We need to take some proactive measures to preserve soil moisture. So let's now come to the topic, engineering the unsaturated soil behavior. So we understood drought, we understood how it impacts the soil moisture. Now let's find a connection between soil moisture and unsaturated soil behavior. So how much the soil moisture is lost is generally a characteristic of unsaturated soil or partially saturated soil. So the signature of unsaturated soil behavior for a given soil, it is represented in terms of soil water retention curve, SWRC in short form, which is a relationship between volumetric moisture content and soil suction. So it's something like this. So you see that red curve, which is called drying curve. Y-axis you have VMC, x-axis it's soil suction. Soil suction means it's a negative pore water potential. As the soil dries, it increases. So it represents the ease with which soil moisture is lost during drying, and it is dependent on the nature of drying, SWRC. So how much water gets lost can be understood from the nature of this SWRC. So an increase in suction indicates drying of the soil. As you can see, as y-axis increases, it shows drying. A steeper slope of this curve means there is a quick loss of soil moisture. I will not go into the details of it. As you can see, for a very small change in suction, the change in volumetric water content will be quite high if it is a steeper slope. So these are some of the SWRC features which are relevant to plant growth and agricultural drought. The first one is called field capacity, where you have sufficient...
please conclude in 2 minutes.
2 minutes, okay, fine. Okay, so I'll just like to state that these are the parameters: field capacity FC, permanent wilting point, and the plant available moisture content, which is shown in that. Okay, so field capacity corresponds to 33, and permanent wilting point up to 1,500 kilopascal. So what it meant by engineering the unsaturated soil behavior, I'll show here. So you have the red curve, which is the original SWRC, and a modified curve, which is blue, and you can see the shaded portion. You are increasing the moisture holding capacity of that particular soil. So you mean engineering means how much of this shaded portion you can achieve through some additives. So here the additives, we talk in terms of water absorbing polymer, which looks something like this. This is the original one. When it absorbs water, it can store water up to 100 to 500 times its own weight. So it's a kind of a polymer. I'll skip this. So this is how it works. When rainfall or irrigation is done, it absorbs water within the soil. Later, when it is dry, it releases back to the soil. So this is the engineering what we have carried out. When you apply the water absorbing polymer to the soil, you can see that from the red dots, it goes up to the black triangular curve, and so much of the amount of volumetric water content gets added up to the soil, which can be later used by plants during drying season. Okay, so the same is shown here in the second plot. You can delay the wilting of the plants. Sorry. So this is the summary and future direction. The essence of this is there is possibility of engineering the soil behavior to have more soil moisture into it, so that even dry condition you can sustain vegetation for a longer duration. So with minimal frequency of irrigation, the vegetation growth can be obtained, so you save a lot of water. So this is just one success story. Even without any sort of engineering aspect, this news came just a few days back, 29th September, where Padma Shri, this particular farmer, Sundaram Verma, he is instrumental in generating growing around 60,000 trees under drought condition in Rajasthan district, where just 1 liter of water was used for the entire lifetime of that particular tree. So he developed a specific method for preserving the soil moisture without any sort of additives. So it's a very good success story which was reported recently. With that, I will conclude the lecture. These are the acknowledgement, and thanks to the organizers of Geotech Asia. Thank you.
Yes.
If you have any quick questions,
Thank you,
we can
Professor
take one.
Sridev. So we can have 1 or 2 questions from the audience.
Sir, it was really wonderful presentation. Thank you for such a good presentation. So, sir, actually my question is like, have you observed any effect of these waves under wetting drying cycles or something?
Yes.
Like, will it be like same water holding capacity after certain cycles, or it will reduce or something? What is expected?
Yeah, that's a very interesting question, because this is one very important aspect of this WAP behavior. Once this wetting drying cycle starts, it undergoes degradation in its properties. So this is not a one-time application of WAP. So this is one particular aspect of future research to understand what should be the frequency by which you need to replenish WAP into the soil, because it will further degrade and lose the entire water absorption capacity. So this will be more like how you do fertilizer into the soil for nutrition. So similar kind of strategy may have to be followed for this, Maybe after 3-4 years, you may have to replenish it again with VAP.
Sir, I have one question.
Yeah.
And really it is very interesting presentation and very much required because we are facing lot many droughts and we are going to face in future also. Sir, my question is what is the effect of urea application or any kind of fertilizer application on this polymerization?
Yeah. In fact, it is not going to affect polymerization as such because it is already polymerized and the polymers are used in soil. So we also had this doubt because salinity is going to affect the water absorption of these polymers significantly. So we have also conducted similar kind of whatever you have asked, what is the effect of fertilizers in the soil on the water absorption capacity. We found that some reduction is there, but it is not as significant as like inorganic salts. So still you have sufficient water absorption capacity for these polymers in the presence of fertilizers. We have checked this. For common fertilizers, we have checked.
Thank you, sir.
So any more questions? Okay, thank you. Thank you, Professor Srideep.
Yeah, thank you. Thanks for all the audience for attending the lecture. Thank you.
Yeah. So now we'll move forward with the presentations. So we have 5 presentations for now. So first I would like to invite Jeremy Torsey and Erika Pina Howald for his presentation on freeze-thaw testing of gabion retaining walls on Cantonal Road 257, Switzerland. Please. So all the presenters will have 9 minutes. So please try to stick to the time.
Thank you. So, hello everyone, my name is Jeremy Tosh. I work at the High School of Engineering in the Canton of Vaud in Switzerland. And today I would like to talk about freeze-thaw testing of gabion retaining walls on the Cantonal Road 257 in Switzerland. I'd like to start this presentation with a short introduction, then the methodology employed for this study, and lab analysis, in situ observation, and finally a conclusion. The Cantonal Road 257 links the city of Fleurier to Sainte Croix on the west of Switzerland. The elevation was between 1,000 meters to 1,050 meters. And this road was protected by old retaining walls, and these retaining walls were replaced in 2016. After a few months, we constated a very rapid degradation of the rocks inside the gabion meshes. When these rocks wasn't no compliance with the current standards in Switzerland. That's why we replaced it by 2 another series of gabion. In 2017 by series 2 and in 2021 by series 3. The rocks origin came from 3 different quarries. But after a few years, the series 2 and series 3 presented a very new degradations, as you can see of the picture. This picture was taken a few years after the installation of the gabion. But the first sensitivity test was confirmed the compliance of the series of the gabion for the rock. That's why the primary objective of the study was to assess the susceptibility of the gabion rocks to freeze-thaw conditions. To perform this objective, we did 2 different experiments. One in situ analysis and the other lab analysis on gabion series from series 2 and 3. To document the degradations of gabion on the road, a monthly assessment was conducted from April 2022 to April 2023. 6 cages were randomly selected, 3 from Series 2 and 3 from Series 3. As illustrated on the figure, we divided the gabion cages in 3 parts: the top vertical front, the middle horizontal front, and the lower vertical front. The top horizontal front was excluded from the study because it was covered by ice and snow during winter period. At the beginning of each month, we went to the road to constate the degradation and take photography. Then we categorized the rock into one of the 4th classification, so intact, no visible damages on rock, light cracks, 1 or 2 minor cracks, advanced cracks, multiple cracks visible on the rocks, and destroyed. The rocks was completely destroyed. Then a percentage of each class was calculated relative to the gabion's visible faces to see the evolution of the degradation through the time. The another analysis was the lab analysis. I would like just to remind the current standard for frost sensitivity in Switzerland. We only test the 8 to 16 millimeters fraction on the aggregate, which is not representative to the gabion size. The rock element was submerged in water and was subjected to freeze-thaw cycles. After completing 10 freeze-thaw cycles, the test sample is sieved with an aperture of D divided by 2, and the mass loss was measured. And we calculated the factor of F. It's just a percentage of the mass loss. So for this study, we changed a few things for these standards. The first thing is the size of the element. We selected the 40 to 100 millimeters fraction directly on the gabion cages. And another thing we changed is the number of freeze-thaw cycles, because we have some temperature sensor on the road, and we have noticed that during the month of April 2023, this data revealed that 11 freeze-thaw cycles occurs within one single month. That's why we increased the number of freeze-thaw cycles to 75 with a control at 25 cycles, 50, and 75 cycles. Tests were conducted using a saline solution with different concentration to simulate the de-icing salt used during winter period. We use a 1% saline solution and 5% saline solution concentration for Series 2, and only 1% saline solution for Series 3. Of course, we also performed the test without any saline solution. Just before, this is the freezing curve used in the climatic chamber. So we started the test at 20 degrees with a decrease to 0 degrees, a stabilization, and then a new decrease to minus 17.5 degrees Celsius. And then we saw the samples and we restart a new cycle. Here, it's an example of a photography we performed. This example is the middle horizontal front of gabion number 4. With picture taken from April 2022 to April 2023. You can see some example of the evolution of cracks into the rocks, and it's just few examples, but we have many examples like this through the years of observation. These two tables summarizes the results, so the statistic we perform from the photography we analyzes. So the proportion of intact element has significantly decreased during these years, with a reduction of 40% for Series 2 and 15% for Series 3. Faster degradation has been observed in Series 3 versus Series 2. It's possibly due to the advanced initial condition on Series 2, because this series was older than the Series 3. But it's also possible due to a freeze sensitivity of a difference between Series 2 and Series 3 in freeze sensitivity. Edges and bottom faces are the most vulnerable faces to freeze-thaw cycles. Edge-destroyed element increase from 13% for Series 2 and 15% for Series 3. Bottom face intact element decreased by 20% for Series 2 and 23% for Series 3. But the top vertical front presents minimal damages, no changes for Series 3 and only 1% in Series 2. The difference between the behavior in the face is due to the water spray coming from the traffic on the road. The gabions are near the road, and the bottom faces and the edge are subject to water spray. So it's more hydrated, and with the free cycles, it decreases the damages to this face. Here, this table summarizes the value of the factor F we perform on the 5 examples, so with different saline solution concentration and in function of the number of free cycles. After 25 cycles, the mass loss remains low, less than 0.3%, and it's in coherence with the standards, because the standards say we need 10 free cycles.
You have 2 more minutes.
1?
2 minutes.
Okay, it's almost done. After 75 cycles, Series 3 had significantly higher mass loss, 3 to 4.5% for Series 2, and until 2% for Series 3, and the Series 2 has only 2%. Adding a saline solution did not significantly affect the mass loss. For instance, Series 2 with 1% saline solution show a higher mass loss, 2%, than the test without saline solution, but the value is higher than the 5% concentration for Series 2. So the variation is likely due to pre-existing features in gabion before testing. To conclude this presentation, gabion in high altitude in Switzerland is a road environment face significant degradation challenges. Water spray for traffic combined with harsh climate accelerate aggregate fragmentation. Current Swiss standard underestimate the number of free cycles and the size of the element. That's why there is a need to update testing protocol and standards to tailor to the actual high altitude conditions. Further research is required to revise standards and improve gabion's durability.
Thank you.
Thank you for your attention.
So, any question from the audience? Well, thank you. We'll move to the next presentation. So, next one is behavior of marble rock exposed to freezing thawing cycles under quasi-static and high strain rate loads by Naveen M. and Ankesh Kumar.
Hello, good afternoon everyone. Today I am presenting the topic of behavior of marble rock exposed to freezing thawing cycle under quasi-static and high strain rate loading. Coming to freezing thawing cycle is a common and serious weathering factor in the cold region. Why it is a serious factor in weathering conditions means when in the rock mass, when that pores is there, when water is transferred from water to ice, there is increase in volume in 9%. So that increase in volume in 9%, that will generate the tensile stresses and a new fracture in the pore. So due to that, what will happen that the change in parameters in the rock. So what will happen, the change in parameters lead to environment disasters such as landslides, collapse of the structures and instability of the structures. If you'll see from the first figure, due to the freezing thawing cycle, the rock mass is deteriorate, and from the second image, you can see a landslide, and third image, you can see a collapse of the structure due to that freezing thawing cycle over a time. So what are the factors that affecting the freezing thawing cycle? So environmental conditions, that is temperature fluctuations and climate. And coming to the rock mass properties, that is porosity, permeability, and mineral composition, and existing cracks. If rock already having the existing crack, it will accelerate more freezing thawing cycle, and that deterioration will be more, and like presence of water content. If water is more, like more ice formation is going to take place. Due to that, more deterioration is going to take place, and additional factors like vegetation and soil cover and the topography. Coming to like these are the different researchers who worked on the different freezing thawing cycle for the different rocks, and like if you'll see like many researchers who like laboratory they simulated for like minus 20 degrees like for freezing condition, and like thawing condition the 20 degrees they consider, and like most of the researchers they consider for like 4 hours of freezing and 4 hours of thawing. So I also consider for like 4 hours freezing and 4 hours of thawing. So coming to one more aspect, like not freezing thawing cycle, one more thing like regarding that drill burst method is widely used tunnel excavation techniques, particularly hilly terrain. So like what will happen during the blast, the shock wave is like shock wave subjected to rock high strain rate loading. High strain rate is nothing but how the strain is varying with respect to time. So like the material behavior will change under the high strain rate of loading. So such loading can significantly alter the mechanical properties and damage behavior of the rock mass. So if you'll see the right side image, like how the strain rate is varies, like for the static loading, the strain rate is like 10 power minus 6 to minus 5. So for the high strain rate loading, it is come under like 10 power 1 to 10 power 4. So why it is important means like complete behavior it will change, because you will get more like stress, peak stress values during high impact load. So to simulate that condition, that ISRM suggested that SHPB test setup. In the laboratory, if you want to simulate the blast loading related to conditions, so ISRM suggested that SHPB test setup. So what is SHPB test setup means like, this is the SHPB test setup. Here like a pneumatic, like we will apply the pressure from pneumatic compressor to the gas gun, and we will launch the striker bar with the different pressure to create like a different impact on that incident bar. So that is the incident bar and transmitted bar. So when we impact with a certain velocity, what will happen, like some energy will be released. Like if you are having like release the striker bar with a more velocity, more energy that will generate. So that energy, that wave, like in the incident bar, what you will do, you will connect the strain gauges to that. So when we are hitting the striker bar to the incident bar, the wave going to be generated. So we are attaching the strain gauges, one at the incident bar and one for the transmitted bar. So what will happen, like like a striker bar, incident bar and transmitted bar, we are manufacturing with the same material. So we are keeping the sample in between the incident and transmitted bar. So due to the impedance mismatch, because like wave velocity and density completely change. For the sample it is different and for the material is different. So due to the impedance mismatch, what will happen, some of the wave that can be transmitted, some of the wave that can be reflected back. So we are recording that waves, and that we are connected to the oscilloscope. So oscilloscope, what it will do, that strain gauge, we know already it work on the resistance, Weystone bridge. So change in resistance that will capture within fraction of seconds, it will capture oscilloscope, and that will convert it to like a DAC, it will record to the DAC, and we will further do the analysis. So as I mentioned earlier, that wave that can be generated, that is like assumption is like we will take one-dimensional wave propagation theory. So from this, this is the wave that can be generated. So this is the wave that can be generated, incident wave. And after sometimes like that some of the wave that can be reflected back, and some of the wave that can be transmitted. So from the equation, we can calculate what is the force. P1 is nothing but like force that can be generated from like incident, the interface between the incident wave and the specimen. And P2 is the like stress, force that can be generated from the transmitted and the specimen. So that average we can do. So we will get the how much like stress in the specimen we will get to know, and we will calculate the strain, how much strain that will be developed in the specimen, and we will calculate the strain rate, how much strain rate we can generate. So like accurate measurement of the stress from this testing is a problematic. Why problematic means like what are the waves that can be generated that is not uniform. So we need to, like wave should be uniform for the stress equilibrium, because like what are the impact energies coming, so that can be transfer like due to that wave, like smoother, there is no smoother wave means like premature failure is going to take place. So we need to like for make stress uniformity. So like Duffy and Christian et al. In 1970, they introduced the pulse shaper technique to to make waves smoother, and like a few et al. In 2001 and 2000, they found that thicker and larger pulse shaper extended rise time, and like they enhanced the stress equilibrium condition. And like Chen in 2016 showed that smaller copper pulse shape improved the wave smoothness, and Gorankar in 2020 reported the copper shape shorter rise time and maintained strain rate stability. So from all of this, you can see like, however, studies related to freezing time cycle rock using pulse shaper are not studied. So in this study, freezing time treated marble rock from Kishanbag region was tested using SHPB test with the copper pulse shaper with a varying diameter of pulse shaper from 10, 12, 15, and 20 diameter. This is the methodology. This is like objective. So experimentally I did. And these are like preliminary tests, like how the freezing time cycle affect the UPV, like ultrasonic pulse velocity, UCS, Brazilian test, SHPB, that is for different 3 strain rates. And that parameter study is varying for different freezing time cycle. And pulse shaper, different diameters, and type of the rock is like marble. So the parameter of interest like stress and strain response from that. Finally, optimum diameter of pulse shaper. These are the assumptions which I taken for this study. So coming to result and discussions, like here if you can see from the image, the densities like after 20 freezing time cycle, if you see the density from 28.2 to 27.6, it is decreasing. Same thing is happening with ultrasonic pulse velocity, it is decreasing from 5,100 to 4,700. Same thing like UCS and density decrease. Why it is decreasing means like after number of freezing time cycle, material will degrade. But like suppose when like water forms ice, the crack propagate. Again, freezing and thawing. So more deterioration is going to take place. That leads to like after number of cycles, the more deterioration takes place. So that's the reason it is like decreasing. Coming to effect of pulse shaper. This is like, as I told earlier, that wave that can be generated incident, transmitted and reflected wave. So these are for different diameter of the pulse shaper. I consider only 1.56 thickness, like constant thickness throughout. So if you'll see that here, like time, like a rise in time, if you'll see from a transmitted wave for the 20 pulse shaper, for the 20 10 if you consider, for the 20 you are getting more rise width, and for 10 you are getting low rise width. That means like for the 10 when you are impacting, that the wave that can be generated because you are using a small disk. So what will happen, that wave that can be generated, that will move faster and failure is going to take place. If you are using, like why for the 20 it is taking more time means?
You have 1 minute. Please conclude, okay? 1 more minute.
Okay, sorry. So like now I will share like effect of pulse shaper diameter on the stress in response. If you'll see here, like for the 20 if you'll compare for, this is for 5 freezing cycle, that is 10 freezing cycle. If you'll see like for the 10 diameter of pulse shaper, if you'll see that as number of freezing time cycles, stress value is decreasing. Same, this is a different type, shape of pulse shaper, diameter of the pulse shaper. If you'll see like diameter is increasing. And finally, like to conclude that which is optimum diameter of the pulse shaper, we need to check whether it is equilibrium condition or not. So people are like, as per research given by Chen and Song and Zhou, they suggested like transmitted wave is equal to incident plus reflected wave. So for the 12 I got like a validation for the equilibrium interface. So it is well matched. So 12 pulse shaper offers a ideal equilibrium facilitating regulating wave propagation and efficient wave transmission. So this is like effect of striker bar velocity. So when we are launching different waves, velocities I use. So if you'll see as the velocity is increasing, you are getting more strength. Coming to conclusion, increase in freezing time cycle, reduce the density, ultrasonic pulse velocity and UCS values. And pulse shaper with larger diameter mitigates peak state by improving wave smoothing and energy dissipation. Elevated striker bar velocity results in increasing peak stress values, and as number of freezing time cycle increases, the peak stress values decrease from different velocities of striker bars. And 12 pulse shaper is the optimum diameter of the pulse shaper. These are the key reference. Thank you.
So any question from the audience? Okay. And thank you. So our next topic is ultrasonic pulse velocity for measurement of unfrozen water content in frozen soil by Ramchandran Arangadurai, Jeevan Joseph, Velnam Sathusekan, Arun PG, Rahul B and Deepak CK.
Good afternoon, everyone present over here. Myself, Ramchandran Arangudurai, research scholar, Department of Civil Engineering from NIT Tiruchirappalli. Today, I am here to give a presentation on the title, Ultrasonic Pulse Velocity for the Measurement of Unfrozen Water Content in Frozen Soil. Generally, in frozen soil, initially we will be having a saturated soil system. Under that, we will be having soil grains. Additionally, in the voids, we will be filling with water.
when we are subjecting it to sub-zero temperature, that is, when we are reducing the temperature, it will lead to formation of ice lens inside the system. So, though if we are reducing the temperature, the ice lens crystals has been formed, some portion of water will remain unsolidified inside the system even at minus 80 degrees centigrade. So this is termed as unfrozen water content. This unfrozen water content entirely governs the thermo-hydromechanical behavior of the frozen soil matrix. So these are all the factors which is governing the unfrozen water content existence inside the porous media. For example, soil mineralogy, supercooling effect of water, cryosuction inside the soil system, adsorptive forces, presence of salts, it will decrease the freezing point depression, followed by that pore size characteristics. This unfrozen water content, it will be represented in terms of a constitutive parameter, which is termed as soil freezing characteristic curve. Initially, when we are considering the soil sample, at initial zone, we will be having only soil. In the voids, we will be having water content as well as air voids. When we are decreasing the temperature, the freezing it will start, that is the ice lens it will start to form. Further, if we are still increasing the negative temperature, we will reach to a stage that we will have more amount of ice lens, we will be having less amount of unfrozen water content. Mainly, this parameter will be governed by soil type, density, pore size, the organic content which is present inside the which is present with our soil, followed by the pore water chemistry. So, to quantify this phenomenon, I have collected soil samples from the southern part of Tamil Nadu. After soil sample collection, I have did soil characterization, I did particle size distribution, and we did relative density experiment because we have conducted our experiment at 30% relative density. So, to relate that ultrasonic pulse velocity and unfrozen water content, we have used two equipments. For unfrozen water content, we have measured with TDS sensor, that is time domain reflectometry sensor, which belongs to meter group. It will directly give us the volumetric moisture content value and temperature. Followed by that, to test the pulse velocity, we have utilized this RTUL 460X brand ultrasonic pulse velocity tester. It will give us the time which is taken for a pulse wave to move through a system. From that, we will be measuring the pulse velocity value. So these are all the geotechnical characterization for the samples which have been collected. I have been concentrated only on coarse grain specimens, not gravel. Why? Because gravel is not that much frost susceptible. Sandy samples are preferably frost susceptible according to CRREL report, that is Cold Region Research Engineering Laboratory report. So I have collected, based upon this criteria, I have been collected soil samples with different classification like well-graded sand, which is S1, poorly graded sand, which is S2, then artificially created sand, that is M sand as S3, then silty sand and clayey sand. This is the particle size distribution for the collected samples. Now, to determine this unfrozen water content, we have created an experimental setup, and we will be measuring this unfrozen water content and pulse velocity simultaneously inside a temperature controlled chamber. The experiments were conducted in the temperature from plus 30 degrees centigrade to minus 30 degrees centigrade for freezing cycle. Followed by that, it will be having a single thawing cycle from minus 30 to plus 30. So, we will be having a TDR sensor which will be inserted at the center of the mold. So it will be connected to a data logger which is ZL6 data logger. Followed by that, it will be the value from the data logger, the value will be data logged using a software called as Zentra Utility software. So from this, by conducting these experiments, I could able to find this relationship between this unfrozen water content for the various temperature range was presented here. For example, if you are seeing sample number S1, which is well-graded sand, initially the soil's water content which is near to 0.35. Later, when it is reaching near to 0 or away from 0, it started its transition. Followed by that, it is having a stage which is there is no further water content change is observed. That portion is termed as residual portion. So that, for example, for S1 sample, the residual water content is almost near 0.093. Similar behavior was observed in poorly graded sand also, but in dry M sand we have a little higher residual moisture content. But when the sample is having some fines content inside it, the observed residual moisture content is still more when compared to the well-graded sand or poorly graded sand. Followed by that, we have measured the ultrasonic pulse velocity of the samples. So pulse velocity, to determine this ultrasonic pulse velocity, we will be having these components, one transmitter and one receiver at both ends. The temperature of the specimen will be monitored by using a T-type thermocouple, and it will be connected to a data logger which is shown there. Whenever it reaches to a desired temperature, we will be taking the sample from the thermally controlled chamber, and we will be measuring the ultrasonic velocity. After that, we will be keeping the sample inside the thermally controlled chamber. So like this, we have conducted for all the 5 samples, we have evaluated for a freezing and thawing cycle how the ultrasonic pulse velocity value it got varied. For example, for well-graded sand, it initially the ultrasonic pulse velocity value is 1500. Why? Because pulse velocity value is path length divided by the time taken. In our system, if, initially the soil sample state will be soil plus water, so it will be having lot of discontinuities and gap might be there. So it will take more time for a pulse to travel to that medium. So the pulse velocity value is very less in the initial stage. But when ice is started forming inside the soil sample, it will create some bonding effect between the soil grains. So it is acting as a cementing agent between it. So the time taken for a pulse to travel through a frozen system, it will be very less when compared to the unfrozen system. So the time taken, it will be very less. So the pulse velocity value will be little higher. So for the value will be which is reaching near to 3000. For some samples, it is reaching near to 3500 or 4000. For all the samples, we have been estimated for freezing as well as thawing cycle. So ultimately, we tried to find a correlation between this.
2 more minutes.
Yes, sir. Last slide. Ultimately, we will be trying to find a relationship between this ultrasonic pulse velocity and unfrozen water content. So as we know that when we are increasing this pulse velocity, surely the unfrozen water content is going to decrease. So for a particular temperatures, we try to extracted the values of ultrasonic pulse velocity and the moisture content values from the previous graphs. We try to plot it with various fits. Under this, we have tried from linear fits to non-linear fits. So under a non-linear fit, logistic sigmoidal fit, we have achieved a R-square value which is near to 0.99 stuff. So which is for various grades of soil also, it is having the same R-square value. So as a summary, a consistent reduction in water content is observed for all the soil samples. Similarly, an increase in ultrasonic pulse velocity also happened. Notably, this ultrasonic pulse velocity and the unfrozen water content exhibit distinct hysteresis behavior patterns for both for all the samples at a 30% relative density. At the end, a nonlinear relationship has been observed between ultrasonic pulse velocity and unfrozen water content. These are all my references. Thank you.
Thank you for your presentation. And please.
Thank you, Ram, for your wonderful presentation.
Thank you, sir.
I have a small confusion. Can you go to your table showing basic characterization? Table.
Yes, sir.
Yeah, here.
Yes, sir.
You are classifying your soil sample like well-graded, poorly graded. How?
Well-graded and poorly graded, it is based on CU and CC value,
Where
uniformity coefficient and...
Where is that value?
Okay. Sorry.
Without showing the value, how can you?
Yes, yes. Sorry, sir.
Okay.
I'll change it.
And then you are using volumetric water content sensor.
Yes, sir.
So that sensor works based on what model, what theory? Do you know?
Topps equation.
In terms of?
Dielectric constant or permittivity of the medium.
And what about suction, soil suction?
Soil suction, there is a different sensor which is Terras 21. It is a different sensor, sir. I am using Terras 12. It is Terras 21.
Okay. So now, a small query. Can volumetric water can be 100% or more than 100?
By definition, it is volume of water divided by total volume, so it can't be more than 100.
Yeah. And what about gravimetric water content?
Gravimetric water content, it can be more than 100.
Like?
Yeah, it is measured in terms of weight. So weight of water divided by weight of solids. So we can have more than 100.
Wonderful. Thank you, Ram.
Thank you, sir.
Any more questions? Okay. Thank you, Ramchandran.
Yes, sir.
Okay.
Thank you so much for this opportunity.
We will move to the next presentation, performance of thermal conductivity models for saturated fine-grained soils by Arjun Sivaprasad and Prasenjit Basu.
Good afternoon all. For the next few minutes, I will be talking about one of the soil parameters, soil thermal conductivity, and its measurement method, how it is used in the application, and one of the models we proposed, and also how it can be used in the field conditions in a numerical framework. Moving forward, defining the thermal conductivity, it can be simply said as the ability of the material to conduct heat. So like that we can feel like when two types of materials are there, like if you are heating from one side, like how the heat is going to flow in that material, and that depends on the thermal properties of the soil. And that is for solids. And when it comes to porous media, so it depends on like whether it is a fine grained material, a coarse grained material, and whether it is a two-phase system or three-phase system, depending on the amount of air and water in it. So because of that, there are lots of factors affecting the thermal conductivity. So it can be intrinsic factors, it can be extrinsic factors. So and depending on that, the thermal conductivity can vary. So this thermal conductivity is a critical parameter in geothermics. So when it comes to the design and performance assessment of the subsurface system, where it is working based on heat transfer in soil, like this is a critical parameter in energy geotechnics field, cold region geotechnics field, and environmental geotechnics. So how it can be measured? So there are two types of measurement method. One is transient state method and steady state method. The transient method is based on the infinite line source theory, and steady state is based on the Fourier's law of heat conduction. So during the measurement, we can see that there are lots of hypotheses based on the differences between the transient measurement and steady state measurement, like whether the direction of heat flow matters, or the volume of soil matters, or what state we need to measure the thermal conductivity. So when it comes to fine-grained material, or especially for saturated fine-grained soil, we can say that there is a unique relationship to void ratio versus effective stress. So that has to be considered when we are measuring the thermal conductivity. So if we need to measure that, we need an apparatus. So we developed our own apparatus. This Energy Geotechnics Laboratory, IIT Bombay, we have developed an apparatus for measuring the soil thermal conductivity at transient state method and steady state method from the temperature time profile from a single test. And also this apparatus is capable of simulating the soil at different effective stresses. So coming to result, quite interesting result is we have used 4 types of soils, fine-grained soils, kaolin clay, red soil, marine silt, and black cotton soil. So it has seen that when the effective stress is increasing, the thermal conductivity values were increasing. So it is clear that qualitatively, when the consolidation is happening, the particle will come close to each other, then the heat conduction can be more, and accordingly soil thermal conductivity will be more. That is qualitative. But how much will be the increase? So quantitatively, how much it can increase? So when we did the regression analysis based on the results, it has been also observed that we were able to correlate the thermal conductivity of soil with the consolidation parameters of the soil itself. So especially the compression index of the soil, lambda, and swelling index, kappa, and over-consolidation ratio, and in fact, pre-consolidation pressure of the soil as well. Professor Sudhi was talking about the significance of moisture content. in the thematic session. So we also, for when it comes to fine grained soil, like moisture content effect will be different for different types of soil. So we correlated, in fact, the consistency index with the thermal conductivity for soil which is coming under different mineralogical group. So that was also giving good correlation with thermal conductivity. So we did also a model comparison with the existing literature. So it has been seen that, okay, if you are just considering just a dry density or a water content or even a just random combination of both, it may not predict the thermal conductivity as it varies with the effective stress. So because in most of the literature, the stress state and stress history were overlooked. So it is important to consider the consolidation parameters of the soil, like whether, as I mentioned earlier, like it is a void ratio versus effective stress matters. So based on the results, we did numerical simulation as well. Like we in fact modeled a borehole heat exchanger up to 70 meters, and then we input this model what we have developed based on the lambda and kappa of the soil. So it has been seen that, okay, rather than taking if you are taking a single value of thermal conductivity and a stress dependent thermal conductivity, how the soil thermal conductivity profile can change. So accordingly, the interesting result was like the performance of the borehole heat exchanger. In fact, the power output from the borehole heat exchangers is a function of equivalent ground thermal conductivity, what we obtained from the numerical thermal response test, in fact. So moving to conclusion, like it has been clear, it was observed that the thermal conductivity can be defined as a function of effective stress, the consistency index, and the consolidation characteristics of the fine grained soil, in fact the compression index and swelling index. And the thermal conductivity we obtain from the transient state and steady state is increasing with effective stress, OCR and pre-consolidation pressure. And also we have to make sure that like performance of a geothermal heat exchangers, it depends on the equivalent ground thermal conductivity. So it is important to consider the equivalent ground thermal conductivity to assess the performance of the geothermal heat exchangers. Like if you are not putting a proper value, either it can underestimate or overestimate the performance of the heat exchangers. Thank you. Also, I am very much happy that I am able to present this work in front of Professor Sridip, who is one of my thesis reviewers. Thank you all. Thank you all for listening.
Thank you, Arjun, for finishing ahead of your time limit. So yeah, we can take some questions.
Okay. So thank you for your wonderful presentation. So if I ask you, what do you mean by OCR?
It is over-consolidation ratio. So when it comes to soil mechanics,
definition,
it is a ratio of how much the soil effective stress, how much the soil is experienced in the past to the present effective stress.
So can you categorize your soil depending upon the OCR value?
Basically, if it is OCR is equal to 2, we can say it is lightly over-consolidated, and if it is greater than 2, we may say that highly over-consolidated soil.
And if it is less than 1?
There is no less than 1. It is can be said under consolidation.
Less than 1. That is under consolidated.
OCR is equal to 1 when we can say that normally consolidated, and if it is OCR less than 1, it is still under consolidation. It is undergoing the consolidation. Yes.
So things are there. Less than 1, equal to 1, greater than 1.
Yes, it's clear for me.
Yeah.
Yes.
Heavily consolidated, lightly consolidated.
Yes.
So it's you are right to some extent. So heavily consolidated soil?
Heavily consolidated soil, mostly based on the value, we say that OCR is greater than 2. It can go up to any value depending on the effective stress.
Actually, it is between 4 and 10. More than 4.
Okay, thank you. Thank you for the information. Yeah.
So, okay. Thank you.
Okay.
Any more questions?
Thank you very much. Interesting the presentation. I have a question. That's the soil material specimen, saturated constitution. Saturated constitution.
Constitution.
Unsaturated or the saturated.
A saturated fine grained soil.
And
yes.
Heating up, thermal heating up.
Yes.
Inside, poor water pressure.
Yes.
Excess poor. I think so. That is growing up with the poor water.
Yes.
Do you think about the measurement to the pour water pressure?
No, sir. In fact, yes, there should be increase in the excess pore water pressure, but we didn't measure the value of pore because the PPT was not there, so we didn't measure the development of pore pressure.
Okay.
Yes.
I think please next time your measurement was a consideration the influence of the pore water pressure. Thank you very much.
Oh, yes, thank you, sir.
Well, so if there are no more questions, we'll move to the next presentation. Thank you, Arjun.
Okay, thank you. Thank you.
So our next presentation is on influence of heating on swelling pressure for bentonite sand mixture with suction control by Tomoyoshi Nishimura.
Thank you, Chairman. My title is the influence of the heating on the swallowing pressure for bentonite sand mixture with suction control, and the term suction control meaning that the comparison and unsaturated condition and the saturated condition. Let's go to the my presentation. This is the background. I think so that the thermal, hydraulic, mechanic chemical phenomena is very important for the detail the radioactive disposal barrier system, and so previous work Horstman at 1999 conduct out laboratory experiment and check the gas penetration for the water saturated buffer. Next one, 2008, Bergerson and homogeneously and the isotropic model for pressure responsibility saturated bentonite with the heating. And the report has the advantage is the one single function and using the prediction model. Next one, Professor Kwai, 2001, and effective gas penetration gas breakthrough pressure for the bentonite specimens. And they try to the temperature 20 and 260 and cyclic. Some number of the cyclic and check the gas generation. So my purpose is the gas for the pressure generated by the heating. And next is the swelling pressure sinking for bentonite sand mixture, unsaturated condition and saturated condition. And so I going to the soil material, Kunigal Boiwan and the bentonite GX and the mixed silica sand and dry density and some dry density prepared from the 0.8 to 1.6. This is the special system, and as you know that the very strong stainless mold and prepared the and very highly temperature heating resistance sensor and lateral surface and check. And this material steering model inside the oven system and apply to the and 60, 70, 80, 90 temperature. Next one. And another one for measurement of the swallowing pressure, as you know that and outside acrylic and chamber, inside is a steel mold, double style, and top is a black frame is the fixed, and the reminding the volume change and with the heating. And below the frame and preparing the road set and measurement of the swelling forces. And this developed the oidometer apparatus inside to the oven baths. Oven baths have their silicone oil. Silicone oil is the advantage and less the evaporation with and according to the increment of the heating. Next one. I'm going to the result gas pressure and for cleanable one and dry density and power pressure and white square unsaturated condition, another one and saturated condition. As you know that the saturated condition and large and poor fluid pressure than the unsaturated condition. Next one, for the bentonite GX, similar to the tendency and white square unsaturated condition, saturated condition with this water and measuring the poor fluid pressure larger than the very is clearly. Next one, swallowing pressure. Firstly, okay, and measuring the unsaturated condition at 60 temperature degrees Celsius. Next one, and saturated condition. How to the saturated condition is applied to the and develop the oidometer chamber inside and apply to the distilled water and remaining the same temperature and swelling pressure very quickly the increment after 60, 70, 18 and 19 degrees. As you know that the remind the increment of the swelling pressure. Next one. This is firstly 60 degrees. And next one, remind the unsaturated condition 70. However, that 18 when the 18 degrees swelling pressure decreasing, that causes is the and due to the heating volume shrinkage. Volume shrinkage is the and negative to the swelling forces. Like this is a reduction. And going to the remind the increment to the 90 temperature, remind the swelling pressure. Next one, apply to the saturation. Saturation is and bring to the increment the swelling pressure. Okay. Next
Sir,
one.
you have 2 more minutes.
Okay, thank you. I'm sorry. This is the conclusion. The gas generation heating is a very swelling pressure was very nice mixture. Thank you very much so much. Thank you.
So finished? Okay. So thank you, sir. Any question from the audience?
Yes.
Yep.
Thank you for your nice presentation. So you have used bentonite, right? Types of bentonite, like is it calcium bentonite or sodium bentonite?
And sodium type bentonite. Kunigel V1 is the sodium type.
Yes. And what about the basic characterization? Basic characterization. Have you done that?
Yes.
Like Atterberg limit calculation, measurement.
Yes.
Then free swelling index. FSI, free swelling index.
Swelling.
Free swelling index.
Now is have
You don't know.
I don't
Shrinkage limit, liquid limit, plastic limit. Any idea?
So Just the bentonite is highly so liquid. Now is forget the physical property information. I'm sorry.
So you have not measured.
Yeah.
So that thing should be measured when you are doing this big research. The
Okay.
basic things should be
Yeah.
evaluated.
Yeah.
So that is missing. I don't know if you have done and not showing. So that should be done,
Oh.
conducted. Basic characterization.
Basically.
Okay.
Okay.
So otherwise it's very fantastic. Thank you.
Oh, thank you very much. No.
Any other question? Okay. Thank you, sir. So, our next presentation is on effect of freeze-thaw on compressibility behavior of fine-grained soils by Majid Hussain, Prashant Singh, Mohammed Samir Dar and Ashish Kumar. Please start.
Hi, good evening everyone, good afternoon. So I'm Majid Hussain and this is the work that my undergraduate students at BTech level had carried. Effect of freeze-thaw on compressibility behavior of a fine-grained soil. So this is a brief outline of the presentation. So introduction, if we look at the freeze-thaw, it's a cyclic process of freezing and thawing of pore fluid, which is most of the time is water. And when you have some environments where you have some salts present, then it can be saline water or some contaminant loaded water within the pores of the soil. Generally, whenever there is this temperature variation, it goes sub-zero, and in the next season it goes above the 0 degree temperature, then there is subsequent freezing and thawing respectively. So if you look at the mechanism of this freeze and thaw, so first there is actually this water migration and ice lens formation. So what happens at the soil that is in contact with the air, it actually first undergoes this freezing, the temperature drops below sub-zero, and this actually creates a suction which is known as cryosuction, and it actually now attracts water from the deeper layers, causing the frozen fringe to actually expand and leads to generation of the ice lens formation. Now we know that the water, when it freezes, it expands by 9%, the pure water. But whenever it is in association with soil, the soil, ice and water interaction actually suppresses it around to 8.5%. And this actually causes expansion and structural damage to the soil structure, to the weakening of the contact force. And once the temperature rises, the ice thaws and it leads to thaw weakening, or we can say thaw settlement. So if we look at the frost action, there is a phase change of water in the soil skeleton. Then frost heave, because of the volumetric expansion of the water within the pores, there is heaving. And then frost penetration, it is a term which actually tells you up to which depth the effect of frost action will be there. These are the schematics showing the freezing of the water, the soil particles that are present, the ice crystals, and the unfrozen water. Now, if you look at the effects of this freeze and thaw, key impacts are there is effect on the foundations, effect of the roads, or effect on the pipelines. You can say each and every civil engineering facility is affected. We have volumetric expansion during freezing, which causes structural damage or disruption. Then thawing, it leads to the settlement and reduced load-bearing capacity. So if we talk about the relevance, it damages the structures, it causes distress, leading to a huge economic loss. So these are some schematics showing how this freeze actually damages the structures. You see there are cracks, there is uplift of the foundations, and that is actually concentrated sometimes on the one side because water content is varying, it is not heterogeneous. Then you see these cracks because of the settlement in the walls and this approach road being settled. We can see the damage on the pavement cracks are there. In C, we can see landslides also, because whenever there is this thawing, because of the rise in the temperature, it saturates the soil, leading to the soil weakening and causing or accelerates the failure of these slides, leading to landslides. Then in C, we can see how frosty heave has actually raised the pavement, and then thaw settlement creates depressions along the roads. Now, if we look at these oil pipelines, there can be axial movement along the longitudinal axis of the facility. There can be vertical movement. There can be buckling if it is constrained, particularly these pipelines in the Canadian region are affected. So if we look at the knowledge gap, we have a couple of presentations that particularly focused on the one extreme of the soil, that is rocks. And this one actually focuses on compressible soil, a clay soil, low compressibility soil, and we focused on how this freezing and thawing affects the compressibility behavior. Looking at main parameters, we have compressibility index, we have coefficient of consolidation and pre-consolidation pressure. The methodology that was adopted, we have a soil sample that was characterized for basic geotechnical engineering properties, classified. After that, its compaction characteristics were determined, and we selected some compaction states that are relevant to civil engineering, like 95% of OMC on the wet side and of MDD on the wet side and dry side. Performed 1D consolidation tests on specimens that were subjected to freeze-thaw and freeze-thaw cycles. And then the parameters that were shown in the previous slide, they were actually examined. This is the compaction curve of the tested soil. These are the parameters, and it was classified as a CL type soil, a good compressive strength, you can say. Then stringage limit was also fine. This is how it actually is placed on the plasticity chart. It is classified as a lean clay or clay of low compressibility, CL soil. This is a typical consolidation specimen, 60 mm diameter, 20 mm in height, and we have three compaction states, one at the OMC MDD, second at the 95% of MDD on the dry side, and the third one on the wet side. So for each compaction state, we have three specimens that were tested. Normal specimen, that is, it was not subjected to any freeze-thaw. Then we have specimen that was subject to a freeze-thaw cycle of 24 hours. These were the parameters that are actually relevant for the compressibility analysis. They were actually evaluated. These are the results showing, which I will actually see how in table they got. So if we look at the results here.
You have 2 minutes.
Yeah, sure. I will conclude in 2 minutes. So this is how the settlement is actually affected. If you look at the settlement, an overall increase of 33% in settlement due to freeze-thaw cycles. Reason being that 99% volumetric expansion of water, which actually then thaws and causes the saturation, or you can say loosening of the soil's structure, microstructure. Then if you look at this void ratio change, which is actually settlement in terms of specific volume. So because of the microstructural breakdown, ice-lens formation, pore expansion, we have high or increased pore over this void ratio. If you look at the coefficient of compressibility was maximum for soil subjected to freeze-thaw cycles as compared to the normal soil. Volume compressibility also, there was 30% increase. Once again, same reason being disruption of the soil matrix and the particle rearrangement. If you look at the main compressibility parameters, very highest for this FT specimen, that means if soil is being subjected to freeze-thaw cycles, the compressibility index, compression index increase means high settlement. This overall, there is this decrease in volumetric, this coefficient of consolidation. So if you look at these key findings that are highlighted in the slide, compression index maximum in freeze-thaw cycles. So overall, if you see, except this pre-consolidation pressure, everything is actually negative impact. And there was a slight improvement in around 7.5% in the pre-consolidation pressure, which could be actually attributed to because this ice is very stiff, it exerts pressure, radially it is constrained, and because of that, a slight increase in the pre-consolidation pressure. Otherwise, settlement increased, reduced rate of consolidation, or are negative. Thank you.
Thank you. So any question from the
Yes.
audience?
I have some small confusion. Can you go to slide number 12?
Yeah, here.
Yeah. You see density
Yeah.
for dry side and wet side.
Right.
1.672, again 1.672.
Right.
Would it be same or different?
It is same. That's
But-
why it is written same. So if you look at the compaction curve, you draw a horizontal line. We have same density, different water contents. One is on the dry side, another is on the wet side.
How?
So let me show you. Can you go one slide back? Yeah, here. So if you draw a horizontal line,
Yeah.
95% of MDD, that will have same density but different water content.
Yeah, exactly. So how you have calculated CC, compression index?
So it is from the analysis.
That I understood. You are right. Density will be same.
Yeah.
Okay.
So from the analysis of the results, you have a equilibrium dial gauge reading under each load. Then you draw E log P, and you find the slope of the virgin this curve, consolidation curve, E log P.
Consolidation index I'm asking.
Yeah.
So in terms of liquid limit?
No, that is a correlation. That is a correlation.
Yeah.
That you cannot use here. So it is a direct parameter from the consolidation test.
Yeah.
What you are talking about, that is 0.09 liquid limit minus 20. That is a correlation, not relevant here.
Yeah. And regarding your AB and MB, AB
Yeah, right.
and MB,
Right.
they are related, right?
They are related because your MV gives AV by 1 plus E naught.
Yeah, no, exactly.
Yeah, those are just information points. That's right.
Yeah. So regarding, this is about bentonite?
No, this is about a real soil that has been actually collected from NIT Srinagar campus. Because last weekend we have a snowfall there, so now till February we will have these alternate freezing and thawing cycles. So this study was carried by my undergraduate students.
So for this, you know, it's important
We are
to...
actually running out of time, so we request you to take it.
Okay, okay.
Yeah, we will
okay?
discuss.
Thank
case
you.
You can discuss later.
Yeah, we can discuss later.
So you're Majid, right?
Right.
Thank you.
Professor Samadhi, I think, has a question.
No, it is not a question, just one observation.
Right.
Now, you have conducted compaction test as per IS 2720.
Right, yeah, lightweight compaction.
So that is not a standard Proctor. That is IS
lightweight, right, yes, sir.
So we should use correct terminology.
Right, sir, IS lightweight.
Because the specifications for standard compaction,
They are slightly
standard
different.
Proctor and IS light are different.
Yeah, slightly they are different.
Okay.
Sir. Yeah, yes, sir.
So that mistake we normally make. So it should be IS light.
Lightweight, right.
Okay.
Right. Yeah, thank you, sir. Thank you very much.
Okay, thank you. So we have one last presentation on, thank you. A comparison of the stability of slope in Chamoli, Uttarakhand using LEM and FEM by Vipendra Singh, Hemant S. Viswas A. Sawant and Yamini Jala.
First of all, thank you, Chair.
Himanshu.
Okay. Okay, so this is okay. So I am presenting the topic of comparison of stability of slope in Chamoli, Uttarakhand using LEM and FEM. Basically, this is the work from Vipendra Singh and Professor Chore. Okay, this is the outline of my presentation. So just to briefly introduce the problem, so we are here discussing the problem of the Uttarakhand area, basically in the where there is this continuous problem of landslides, and particularly during the rainy seasons. Once there is a monsoon or rainy seasons there, many landslides are occurring in this region. The reason being that the landslide is occurring is that first of all it is in dry state, maybe in the unsaturated conditions, and after the rainfall again soil becomes saturated, and that may trigger the landslide. The factors is like steep topography, the slope is in the range of 40 to 47, 50 degrees slope. Then there is overburden over the rock mass, and there is obviously this continuous movement of Indian plate and towards the Eurasian plate. And because of all the three activity and during the rainfall, there can be landslides, and which can be explained in the future slides. Okay. So to here what we have done is we have taken the area from Chamoli, Uttarakhand near the Gopeshwar town, and this area there was landslide was occurred, and that was analyzed. What was the reason behind it? Okay, so this is the area of this Chamoli, Uttarakhand. You can see the geographical location of this latitudes and longitudes here. It is the Haldapani landslide in the Gopeshwar town. This study area falls within the Lesser Himalayan zone, and this is mainly composed of metamorphic and sedimentary rocks such as phyllite, schist, and quartzites. Okay. We'll move to the next slide. So you can see the movements occurring in the particular location. You can see the Google's images from the Google Earth from 2011 and to 2021. It was started moving around in 2013, and you can see the movement is quite significant in the images taken at June 2021. Okay. So what we have done is in the methodology, we have collected the samples from the particular landslide area, and these samples were taken to the laboratory of NITJ, and it was tested for shear strength parameters. The approximate geometry was prepared from the Google Earth images here. You can see that so there was a movement was occurred of nearly 4 to 5 meters in the landslide zone, and the slope was observed to be around 40 to 47 degrees. So we have taken average slope of 45 degree here, and we have taken the average overburden debris was of 10 meter thickness. So this slope was modeled using the GeoStudio softwares. One is Slope W, that is the limited equilibrium method, and second is Sigma W, that is based on the FEM. So in the case of Slope W, we have used the Morgenstern price method, and in the case of course FEM, we have used for continuous strength reductions. So these are the parameters used for LEM here. You can see there are C and 5 for the debris, and corresponding C and 5 were 55 C for rock, and 35 angle was taken here. Okay. And for limit equilibrium, for FEM, for the rock modeling, we have used the Oak and Brown criteria, where you have used sigma Ci as 50 MPa, and GSI was taken as 35 to model the Oak Brown criteria. Okay. So we can see the result. We can discuss the results now. The factor of safety was found out from both the analysis, from sigma W as well as from
slope W and sigma W. The factor of safety obtained from the slope W analysis was quite low. It was 0.87, that too for static conditions, and factor of safety obtained from the sigma W was in the range of 1.019. So in the case of sigma W, what we have done is we have changed this strength reduction factor from 1 to 1.2, 1.4 and so on, and we find out at which the factor of safety or there is a sudden movement of the displacement. So it was triggered at something like near to 1.019. We can have contours also in the next few slides. So this was the factor of safety from slope W and sigma W, 0.87 and 1.019. And the next few slides we can see that. So when we change this SRF, so displacement was very small when SRF was equal to 1, there is no reduction, but when it was changed to 1.2, the displacement was to the tune of 0.55 meter, and it was going to be very high for the further increase in the strength reduction factors. So we can see that the sharp increase was observed at the 1.019, and that is taken as the factor of safety for the sigma W analysis here. Okay, you can see the displacement contours over here for SRF equal to 1.0 and 1.2. You can see that the maximum displacement for 1.2 is going to the tune of 0.55 meter here. So already failed. So because it was already failed in the static condition, so it was not tested for the pseudostatic condition, because already it was showing a very low factor of safety as something like 0.88. Okay. So these are again the displacement contours for the next SRF factors of 1.4 and 1.6. Okay. So further studies are to be taken up. So study is primarily a numerical comparison between the LEM and FEM methodologies under specific static load conditions at a given site. And since it was not stable against static condition, it was not tested for pseudostatic condition. Otherwise, it is a highly active seismic zone coming under zone 5. Already it cannot withstand that much. Okay. So in the present study, the material properties and geometry of Haldapani landslide was done. From both LEM and FM analysis, it is concluded that it is a high risk for debris flow and which is transitional nature. So it should be properly treated for the further protections. And I think that's all from my side. So minimum factor of safety was 0.871 from limit equilibrium, and it was 1.019 from the stress-based stability. Maybe in the FEM, it can take a little bit of proper interface modeling between the two soils, that is the base rock and what is the ore burden. Okay, that's why the factor of safety is a little bit higher in the case of FEM analysis. And that's all from my side. Thank you.
Thank you, Professor Sawant. So any question from the audience? I just have one query.
Yes, please.
Yeah. So for the soil and rock properties you have shown, so what kind of tests were done for the shear strength parameters?
For soils, of course, samples were taken from the laboratory, taken up to the laboratory, and for the rock mass, the rebound hammer tests were collected in situ.
Okay, and in the laboratory, what tests were done for the soil samples?
Direct shear test, DST.
Direct shear, okay.
DST, yeah.
Okay. Thank you. So we have come to an end of the session.
Yeah, thank you everyone. So today we had a wonderful session on cold, coastal and environmental geotechnical engineering, wherein Professor Srideep sir presented on a very important topic, engineering the unsaturated soil behavior for agricultural drought preparedness. We all understand the need for having water retention in the upper layers of the soil. Sir, thank you very much. And after that, we had 7 papers presented in this theme. And I thank all the presenters for sharing their knowledge. And I also thank my co-chair, Swagato Mukherjee, for sharing this session with me. Thank you.
Now I request ma'am to hand over the moment to Srideep sir. now I would like to invite Professor Samadia to hand over the movement to our chair and co-chair. Now the session is over. We close the session here.